Hi everyone, thank you for coming to listen to us today. We're utilizing a Raspberry Pi to make your home smarter team, and I'm Navita Karthikeyan.
I'm Lily Kwok. I'm Sneha Rapali.
I'm Farid Ravichandran.
And I'm Anna Song.
And today we're going to be talking to you about a product we designed, the Eco Shower, and explain how it combines the ideals of water conservation with the practice of home automation. Before we begin though, I'm going to briefly go over what our presentation will contain. When we were first given the prompt for our project, we were given a more open-ended challenge than a lot of other groups. We were simply asked to combine home automation with Raspberry Pis in some way, but we were allowed to design the product as we saw fit. So we began by just simply following the engineering design process. What I mean by that is that we started by brainstorming and coming up with a project idea. Once we had the idea down, we translated it into a project design, which we then built and tested. Once we had the results from that test, we took them, we analyzed them, and we came to a conclusion. Before we go over all that though, we're going to start with that.
Home automation is the ability to control certain aspects of the house through the use of microcomputers and sensors. It works by using sensors to detect human actions and inserting these pieces of data into a home network. Once in the home network, this stream of information is used to dictate automatic actions in the household. As seen in Figure 1, the Raspberry Pi is the brain of the device that is used to accomplish certain tasks and is programmed, and it is used very heavily in the field of home automation. Water is a limited resource that everyone needs, from cooking to cleaning to showering, and simple actions can be taken by anyone to preserve water and are often more feasible than implementing water supply infrastructure. According to the Environmental Protection Agency, individuals use 16.6% of their daily water consumption for showering, meaning that the average family of 4 in the US uses about 40 gallons per day. In total, nearly 1.2 trillion gallons of water are used in the US per showering per year. So the problem that we targeted was that a great amount of water is wasted in showers when the user steps aside to put on shampoo or soap, leaving water coming at a full blast. So combining the concepts of water conservation, home automation, our goal with this project is to preserve water in showers when the user is participating in non-rinsing activities. We will be using a shower mat that functions as a pressure sensor and a solenoid valve unit that will control the amount of water coming out of the shower head. As seen in Figure 3, when the user is standing on the shower mat at B, the flow of water from A should be regular. However, once the user steps off the shower mat at B, the flow of water from A should reduce. And both the pressure mat sensor and the solenoid valve unit will be using Raspberry Pis, and the way that the two Raspberry Pis will be communicating is through two XBs. And an XB is a radio that allows for wireless communication between the two Raspberry Pis.
In order to complete the project in the most organized and efficient way possible, we split it up into 3 major components that we completed individually before putting them all back together for the final product. First, we completed a pressure mat sensor, which detects exactly where the user is standing while taking a shower. Next, we completed the solenoid valve circuit, which controls exactly how much water is released from the shower head during the shower. And lastly, we coded the Raspberry Pis and configured the XBs accordingly in order to make the entire process automated and wireless. Once we had completed these three portions, we then moved on to experimental testing, during which we devised a procedure to test exactly how well our Eco Shower did at conserving water and controlling the rate of water flow.
As seen in Figure 5, our pressure mat sensor consists of a pressure sensor, Raspberry Pi, XB, battery packs, and necessary circuitry equipment. The pressure sensor is the main component, built from 2 pieces of stacked inducting cardboard covered on the insides by conducting aluminum foil. 2 wires connected to each of these pieces complete a potential circuit with our Raspberry Pi, which is powered by batteries run through resistors. In turn, thus, our Raspberry Pi can clearly sense any changes from our pressure sensor and communicate accordingly with the XB attached to the Pi. Under normal circumstances, the 2 pieces of cardboard are separated by another piece of inducting cardboard framework. However, under significant human pressure, when the user is standing on the shower mat, the 2 pieces of cardboard compress, thus bringing the 2 sheets of aluminum foil into contact and closing the circuit. Whether the circuit is closed or open, then the Raspberry Pi sends different signals through XB communication to the solenoid valve unit. Our solenoid valve unit is easily attachable between the shower head and connection through the 2 ends of the valve. It consists of a solenoid valve, a Raspberry Pi, an XB, necessary circuitry equipment, and battery packs once again. The solenoid valve is wired to the Raspberry Pi, both of which are powered by battery packs. The Raspberry Pi is then connected to its own XP, which can communicate to its XP counterpart from the pressure mat sensor. Under normal circumstances, a plunger blocks the inner valve opening in the solenoid valve and blocks any water flow. However, in the presence of an electromagnetic field, the plunger lifts and allows normal water flow. Thus, based on XP signaling, the Raspberry Pi can either run a current through the solenoid valve and completely lift the plunger and allow normal water flow, or send oscillating voltage signals and lift and drop the plunger to reduce water flow and reduce water wasted during user non-rinsing activities.
The central components of our project are the Raspberry Pi microcontrollers and the XP modules. These devices work together to control the solenoid valve's function depending on the signals received from the pressure sensor mat. In our project, we have 2 Raspberry Pis, which are the green devices in Figure 7, as well as 2 XPs, which are the blue devices up above them. XPs are wireless modules that are small and extremely affordable and can transmit signals wirelessly over short distances. They are connected to the Raspberry Pi using the red devices, which are known as USB Explorers, and connect to the Raspberry Pis through the Raspberry Pi's USB port. We have 2 Raspberry Pis in our project, and the first Raspberry Pi is located near the pressure sensor mat, where it is coded in a Python program, and it is coded to receive an electrical signal from the pressure sensor mat when the user steps on it. It will then send a wireless signal using the XP, and the second Pi, which is located near the solenoid valve, will then search for this wireless signal. When it receives and reads this input signal, it will then output a voltage into the solenoid valve circuit and then open the solenoid valve as necessary. Initially, we hope to have all 3 of these components working together in sync in order to have a completely automated prototype working in order to collect data. However, when we were coding our product, our Raspberry Pis could not connect to the computer. Therefore, although we were able to write the code, we were not able to upload them onto the Raspberry Pis, and we could not make the entire process automated. So, what we did is we used a manual procedure instead in order to collect our data. We manually controlled the solenoid valve to control the water flow, and therefore simulated the effects of the eco shower, and were able to collect very similar data.
As seen in Figure 8, in observing the effectiveness of eco shower and water conservation, we conducted experimental testing to determine the comparative flow rates between normal and reduced water flow, as imitated by our solenoid valve. To imitate and achieve normal water flow, we ran a current through the solenoid valve, as said, and completely opened the plunger. However, to achieve reduced flow, we open the circuit and thus drop the plunger 1 out of every 5 seconds in rotation. To open and close the circuit, we decided to disconnect and reconnect 1 out of every 5 seconds the voltage wire of the solenoid valve's power source, the battery pack. In carrying out our experiment, we poured a constant flow of water through the upper end of the solenoid valve and only stopped our timer when exactly 200 milliliters of water were collected through the other end.
Data points were collected over a series of 5 trials in which the time it took for 200 milliliters of water to be released was recorded. Then using this time and the volume of water, the rates of flow measured in milliliters per second were then calculated. As shown in the bar graph, the differences between the normal and the reduced flow rate due to the eco shower were relatively consistent throughout the 5 trials. Therefore, once the percent differences were calculated for each of the trials, they were averaged to be 24.6%, which represents the percent of water that can be saved using the eco shower. This percentage was then applied to an average shower in the United States that can have a flow rate of up to 9.5 liters per minute. Through calculations involving the percent difference, this value was reduced to 7.16 liters per minute. Furthermore, the volume of water that can be saved by an average household per year was calculated and found to correlate directly with the percentage of shower time spent on non-rinsing activities. For example, if a family spends 50% of their showering time shampooing, conditioning, and completing other non-rinsing activities, they can save nearly 6,800 liters of water per year. This demonstrates the potential long-range effects that the eco shower can have in terms of water conservation.
In order to ensure that the data we collected was indeed statistically significant and that our results were not marred by outliers, we decided to perform a test known as a T-test. What a T-test does is it compares the means between 2 different groups. It then takes the result of the test, which is known as a p-value, and it compares it to a benchmark number known as an alpha value. If the p-value you received is lower than the alpha value, that means that the data you collected is indeed statistically significant, which in our case would mean that the eco-shower was effective in reducing the water flow. Once we completed our t-test, we found that our p-value was 0.002047, which is much lower than our benchmark alpha value of 0.05, which means that the eco-shower was indeed very effective at reducing the amount of water that came out of the shower.
Throughout our project, there were numerous challenges that we had to overcome in order to arrive at our final product. The most notable challenge was the Raspberry Pi connection problem, as displayed in Figure 12, which rendered us unable to make an automated prototype. However, we were able to get around this by creating a manual prototype that still was able to collect the data that we needed. In addition, there were also some other problems near the design process, such as determining which sensor would be the most suitable for our project. When we were trying to figure out a pressure mat sensor, we needed to make sure that the sensor would be sensitive enough to sense a person's weight on it, however not overly sensitive to be interfered by the numerous water droplets that would be falling on it. Therefore, we designed our pressure sensor mat in a manner so that it would only react if significant pressure, such as caused by a human on it, would cause it to react, whereas water droplets would not cause it to react and send a signal. In addition, we also had to make sure that our overall product was cost effective and met within our budget constraints. Several of the equipment, for example, sensors and the Raspberry Pis that we found online, were rather expensive, and in order to reduce the cost, we made our pressure mat sensor out of cheaper materials ourselves, so that we were able to have a sensor that suited our needs, but also managed to stay within our budget constraints.
As for the future steps we would like to take with the eco-shower, we hope to one day turn our prototype into a commercially viable product. In order to do that, though, we do need to fix the problem that Varun just mentioned, specifically the one involving the wireless connection issue. As our project does involve home automation, we have to ensure that the Raspberry Pis and XPs are working as we intend them to. Once we fix that issue, we would like to replace the alpha prototype we created, which is seen in Figure 13, with a much sturdier beta prototype. Instead of using materials such as cardboard, we would like to use materials such as plastic, which would be a lot more long-lasting. Once we have our beta prototype, we would like to patent our design and hopefully turn it into a product. In the future, we would also hope to use the theory that guides the eco-shower for other applications. For example, using it in dishwashing to reduce the volume of water used there. The end result of the eco-shower is a decrease in water utility bills for households, a lessening of the amount of water used, and an overall positive impact on the environment.
We would first like to recognize our project mentors from Lockheed Martin, Josh Binder, Kai Caverly, Manu Kolakot, Joe Ippolite, and Evan Keston, and our project RTA, Noah Lee, for their time and guidance during the development of our project. Next, from the Governor's School, we thank Dr. Rosen and Dean Antoine for their continual support throughout the program. Finally, we express our gratitude towards the sponsors of the Governor's School of Engineering and Technology for providing us with the opportunity to attend this program, which has helped us to learn and grow as future engineers. Thank you very much.
I'm not sure I understand how the cardboard tinfoil became a pressure sensor. Can you walk me through that a little bit more?
Yeah, sure. So our initial idea was to create a cost-effective shower mat to go with our solenoid valve because most houses have shower mats, so it wouldn't be an inconvenience to the user. And at the same time, it would detect whether the user is directly underneath the shower head or participating in non-rinsing activities like such as shampooing or conditioning. So we decided it's a binary sensor, so it's very simple. It either sends a signal or it doesn't, whether the user is on it or not. We considered, as Varun said, many other sensors, but this one was the most cost-effective and efficient. So the function of it is there's two pieces of cardboard, and on the insides there's two pieces of aluminum foil taped to the cardboard. And normally it's almost like a sandwich. There's a cutout cardboard framework that's hollow in the center, but has stability on the sides. So when you put it all together, the two pieces of aluminum foil are normally not touching because of that framework. However, when the user stands on the mat, the pressure is significant enough so that the two pieces of cardboard on the outside compress, and thus put the two pieces of aluminum foil into contact. And our pressure mat is also wired to our Raspberry Pi and XP and power sources to complete our entire pressure mat sensor. So when the two pieces of aluminum foil touch, it completes the circuit because the wires are initially attached to only the top and bottom pieces of cardboard.
So how did you limit it only to heavier weights? Just because the cardboard itself it would not bend with water? Is that-
Basically, because the water droplet, the cardboard is too rigid to, if a water droplet were to fall on it, it would not compress enough. But if a person steps on it, it's still like it's more flexible than, for example, wood, which would not bend at all. So would bend if a person stepped on it, but not if like a water droplet.
And how'd you keep the water from completing the circuit?
We would need to waterproof the entire product. So what we actually did, it was a little funny. In order to waterproof, we decided to get large containers of some sort. So we used gigantic Ziploc bags that were like 5 feet tall, and we put everything inside of it. And since the Ziploc bags are flexible, you can still step on it and you wouldn't have any issues. For our future hopes, of course, we would try to replace that with like plastic or something that's a lot more feasible to use in the shower. And just to walk you through the electric circuiting of our product, we did prepare slides for the circuit. So the slide that Anna was just talking about is the one on the right. And so as you can see, there's like a little switch that seems like it's open. So when a person steps on it, the circuit would be normally closed, sending the circuit.
Yeah, so in the future we would hope to actually use an actual shower mat that you would see in your
California needs you now, needs that product.
Why did you choose a shower? Okay, so I think this is a perfect opportunity to involve the audience. So how many of you guys showered in the past 24 hours? Now, how many of you guys think that you wasted shower water when doing so? So personally, I know that when I shower, I don't think too much of wasting shower water when I'm putting soap on or shampoo on. And as I mentioned before, nearly a fifth of daily water consumption is used just for showering. And showering is such a relevant topic in our daily lives because we should be doing it every day. So we thought this would be a great problem to tackle.
It seems the problem with Raspberry Pi, and I can't believe I'm even using the terms because I'd never heard of it 5 minutes ago, but it seems like that was the center of this not working and that you had to go the manual route. How difficult do you think it's going to be to fix that problem, or do you have to use another thing besides Raspberry Pi?
Well, what we think at this point is there's several models of Raspberry Pis to begin with. So like we're thinking that the problem may lie in the fact that we got a Raspberry Pi Model A+. There's also a Model B, and there's several other types. So we're thinking maybe if we tried a different model, perhaps it would work. But the major thing that was confusing us was that when we tried it with 2 Pis, and the same issue happened with both, which is rather interesting for us. But we're thinking perhaps with the new Raspberry Pi that we purchased, we could be able to solve the issue, or we might have to use a particular cable that connected the Pi to the computer. We're thinking we might have to buy a different type of cable that may be able to connect the laptop to the Pi in a better way so that we would be able to alter the code. So honestly, all we need to do is we just need to find a way that would get the computer to recognize the Pi, so that we can just make that little change to the code, add it in, and then then we'll be able to test out the automated version and make any changes as necessary, and we should be good to go. If we had more time, we definitely would have been
Sounds
able to do
wonderful.
that.
How expensive would this be?
So that really depends on our material costs. The materials we use for prototyping were obviously very inexpensive due to our budget constraints, so we use, as I said, cardboard and other such simple materials. In the future, if we would want to use like plastic or something, that would obviously increase the cost. We can't give you a number right now just because we're not sure which materials we would use for our future product, but it should be a fairly inexpensive device simply because it's sort of a do-it-yourself type of device, so you're not making a lot of huge changes. It's a very simple system.
So currently you are using 2 Raspberry Pi. I'm wondering whether you can consolidate all the functions into one.
And to use one Raspberry
One unit, yeah.
1 unit? Well, we initially wanted to use 1 Raspberry Pi, but if we used 1 Pi, we would have to use a lot of wiring, which would be a major issue. So we needed the 2 Pis so that we could have 2 XB modules, and therefore we could make a wireless communication. So we needed 2 XBs in order to have the wireless go from 1 Pi to the other. So that's why we used 2 Pis instead of 1. And we didn't want to have wires in the shower because that would be a very unsafe situation.
I love the phrase non-rinsing activities, by the way.
We spent a lot of time.
Maybe you like it too much.
Thank you.